Welcome everyone to today's One World Probability Seminar. So before I introduce the speaker, just advance notice that next week we have Frederick Vickland and Yilin Wang speaking. Also, just a quick reminder about the way we're happy to do questions. So if you'd like to ask a question during the talk, feel free to just write it in the chat, and other experts in the audience feel free to answer any questions. Otherwise, Alessandra and I will be happy to interrupt Rick and ask him the question direct. Okay, and so that brings me to the introduction. So we're very happy this week to have Richard Kenyon from Yale speaking on the multi-tiling model. Thank you.
Thanks, Amanda, and thanks, organizers. Yes, please don't be shy about interrupting. This is a new project for me and Cosmin, who's I think in the audience, and you know, we're happy to have input about any aspect of the model. And let's see. Yes, I'm lecturing remotely, so I'm going to be looking down. I look down a lot, and I don't get a lot of feedback from the audience, so I'm happy to have any kind of feedback you can give me. Sure. Okay. So this, by the way, right. So Andre Pohada is at Yale. He's a postdoc here. He's my co-author. This is a project we started not so long ago. We started thinking about dimers, and then eventually realized that we can generalize it in actually quite many different directions. But the basic model here is a random tiling model, and not necessarily in 2 dimensions, but my pictures are going to be mostly in 2 dimensions. So what's a random tiling model? Let me just start off very simply. We're going to have a set of tiles, like domino tiles are just 2x1 rectangles here. Right, if you look over here, the 2x1 or 1x2 rectangles, then we have some region in the plane, and we want to know, want to tile that region with the dominoes and ask, what does a random tiling look like? And of course, there are many versions of this model. You can take your favorite set of sort of prototiles, and maybe you can allow rotations and translations, or just translations only. Typically in this talk, we'll allow translations only. And of course, many of these models have been well, yeah, so here's in fact the definition, right? So we have a finite set of prototiles T. By prototile, I just mean some sets in the plane, and a region R, maybe like one of these funny regions in the plane. And then the standard questions that one asks is, well, the most obvious question is, is it even possible to tile our region with, let's say, translated copies of the tiles from T, right? That's, of course, I should say, a hard question already for a general set. It's a, NP hard, NP complete, in fact. And of course, then, if you want to think about probabilistically, we want to we would like to ask, some combinatorial question: how many ways can we tile? If we can tile, how many ways can we tile? That's even harder, of course. And as probabilists or statistical mechanics people, we'd like to understand the structure of a large or possibly infinite random tiling. All right, those are the basic issues that we are thinking about here. And of course, we don't, like I said, we don't have to restrict ourselves to the plane. There are many versions of this problem. Well, okay, but even though those questions are hard, they are very natural from a mathematical point of view or a physics point of view, right? When you make some crystal out of a bunch of atoms, right? That's kind of like what's going on. Or if you make some, if you want to understand the phase transition from a liquid to a solid, this is the sort of standard set. I mean, it's the standard way to model that is one standard way to model that, at least, is through a random tiling model. But even what we find out is that even in the easy cases where we can actually analyze things like this, like some of these pictures here, like the domino setting, has been fairly extensively analyzed. The answer is not just hard, not just complicated, but it's actually involves some deep mathematics, right? They lead to some phase transitions, some conformal invariance business. There's connections with geometry, algebraic geometry, integrability, even string theory, right? So this study of random tilings, which has not been going on well, maybe it's been going on for 100 years, but not really much longer, I guess, has really led to a lot of interesting mathematics and physics. So what I want to talk about in these lectures is an easier version of that problem. So right, the your generic random tiling problem is NP hard, but I want to talk about an easier version, and this easier version will lead to some exact and interesting mathematics, hopefully, for you. In particular, there's some exact enumeration involved. There's some interesting conformal limits, scaling limits. There's some phase transitions, and there's even some quasi-crystals, which sort of arise naturally in the model. So let's see. Before I get started, I want to just tell you one little tool, which maybe you're all familiar with from, at least in your, maybe this is something you learn in your probability class, but I thought it's just one slide of very simple probability about, some problem about the simple random walk, okay, which I didn't know who to attribute it to, but I think, it's safe to attribute it to Boltzmann, right? Because it's really, anyway, never mind. And I learned recently that some people call it exponential tilting. I don't know if that means anything to you, but I hope people are not bored by this, but let me just say it anyway, because we're going to use it shortly. So suppose we just have a simple random walk on a lattice, ZD. And my illustration, for most of the time, I'm going to be thinking about Z2. So let me just, but it works in D dimensions, right? So we have a random variable which consists of one step, which right, and it's a finitely supported distribution on ZD, right? So you can think of that as a step from the origin to a point ij with probability pij. There's a finite number of steps of this simple random walk. And of course, after you take, now we're going to take a sum of n IID variables, xi, each of them with the same distribution. And of course, you end up somewhere in the scaled up copy in the convex hull of the set of your steps scaled by n. Right, after n, I'm just reading the slide here, after n steps, this sum is somewhere inside the n times the convex hull of the initial steps, right? But the law of large numbers tells us that we are going to end up somewhere near the mean value if n is large. N times the mean value of the variable. But I want to ask a different question. I want to consider a sort of a large deviation event and ask what, if I condition the walk after n steps of being somewhere else, like at that red little plus sign, how do I understand that walk, right? What's the probability of reaching there, and what does the typical walk look like that reaches that point, right? So it's just large deviation event, kind of a standard thing. And right, so if you want to condition the walk to end up at a given location plus, which is far from the, somewhere else in that convex hull, then, well, you can achieve the same measure by just adjusting the step probabilities by an exponential weighting. So the original step probabilities are Pij, those are the ones which get you to the ij. You multiply this by this function e to the xi plus yj, where, right, so it's a function which depends only on I and j with these constants, capital X and capital Y, which I'm calling capital X and capital Y. And then of course you have to rescale everything by constant so that the sum of the probability still is 1. Right, so I'm just taking my standard random walk probabilities and I'm sort of multiplying them by an exponential tilt, if you like. That's what the tilt is for. And of course, the theorem is that no matter where, if you choose your point you want to end up, there is an xy, a unique, there's a unique xy, right? So maybe I didn't give all the hypotheses here, but once you choose your desired the location you want to end up, there is two constants, capital X and capital Y, such that the new random walk will have that expectation, will have that as its mean value. Okay. However, if you want to actually, so all you need to do is write down the expectation as a function of X and Y. Unfortunately, you get some sort of nonlinear equations here to solve for X and Y as a function of the destination, desired destination. But there's a certain, Legendre duality technique which will allow you to solve that. So essentially, even though it's a nonlinear equation, you can solve it by minimizing some convex function. Okay, so now let me just define the model. Any questions? I'm not really monitoring the chat, so if there's something interesting that I can help out with, just Amanda or somebody let me know.
Yeah, don't worry, we're monitoring the chat and we'll interrupt you.
Fine. Okay, so here's our model. And we intended it to be fairly general. So we're going to take a graph G. Let's just stick with the finite graph for now. And I'm going to take a subset, a collection of the connected is not so important maybe, subgraphs of G called tiles. So T1 through Tk. So capital T is a set of tiles. Each of these Ti's is a subgraph. You can think of it as an induced subgraph. So just a collection of vertices along with the edges that connect them. And for each tile is going to have a weight W sub T, if you like. Okay, a positive real weight on each tile. Right, so, and, here's a very simple, some simple examples, right? Graph is just a cycle, and my tiles are just pairs of vertices. So, this is like that could be one tiling of the graph, all right? Now what we're going to do is take a blow up of the graph. So we're going to choose for each vertex in the graph, I'm going to choose some multiplicity capital N sub V, which you have to think of that as a large number, but it can be any non-negative real number, non-negative integer. and we think of that as a multiplicity associated to each vertex. And now we're going to make a new graph. So our original graph, G, has some set of vertices, and we're going to make the new graph G sub N here, which over each vertex U has N sub U vertices. And for each edge of the original graph G, I just choose a complete graph connecting if the edge goes from U to V, it's a complete graph connecting the vertices on the left and the vertices on the right, a complete bipartite graph. Right, so the vertices up here, the vertices over a single vertex are not connected to each other, they're only connected along the edges of the original graph G. So let's call that the blow up of a graph. And G sub N is the notation, right? So N doesn't have to be constant from vertex to vertex, but it's, for most of our applications, it will be constant. Okay, so now if we have a tiling of the graph G, right? So, I mean, suppose we have a, sorry, let me go back. Suppose we have a tile now, right? Our tiles are subgraphs of the original graph G, but we can, of course, lift a tile from the lower graph into the upper graph by just choosing for each vertex of the tile, we choose a vertex in the upper graph.
Can I just check, must your tiles be edge disjoint?
The tiles...
the set of tiles.
Yeah, I haven't told you what a tiling is, but let me tell you what a tile is, and then I'll tell you what a tiling is. Okay, a tile is just a subgraph of the original graph, and of course I can lift that to be a subgraph of the blown up graph.
But in the examples you've given, your sets of tiles are all edge disjoint. Is that a requirement? So for instance, you haven't got the subgraph 1, 2, 3.
No, they don't have to be edge disjoint.
Okay.
Yes.
What is K? K and V, what is K? K and V and U, what is K?
Can you repeat the question?
K, what is K?
Where's K? This is the complete bipartite graph when you have a bipartite graph. That's just notation for a complete bipartite graph, KMN, where M and N are the multiplicities of the left side and the right side. Okay, so now, is that okay? Each tile, of course, which is originally a subgraph of G, you can lift it into Gn in many ways. In fact, it's easy to count the number of ways you can lift it. You just choose one vertex over each vertex there, and then the edge is determined. And so let me tell you what a tiling is now, right? Well, okay, I didn't write it down, but all it means is a set of tiles which are vertex disjoint and cover all the vertices of the lifted graph, of the blown up graph. So an n-fold tiling now is going to be a tiling of Gn, which means a partition of the vertices into subgraphs, each of which is a lift of a tile. Is that clear? Okay, so those are the kind of objects we're going to be studying, these n-fold tilings. If you're used to thinking of tiling as sort of a two-dimensional object, right? Like over here, right? You can imagine tiling this graph by putting many copies of each tile on, so that each vertex is covered exactly n times. Right, so here the tiles are going to be translates of these two things, and I can put a bunch of tiles everywhere so that each vertex gets covered with a certain multiplicity, certain predetermined multiplicity. That's the model we had in mind, but our model has a little bit more information than that, because we're keeping track of which vertex above gets covered by which tile, essentially. Okay, let's make sure we get the definition right. So if you have a question about the definition, interrupt now. Otherwise, the rest of the talk won't make any sense.
So Richard, can I ask a question? So you're talking about keeping track of the vertices above, which are tiled. So in that sense, they're kind of labeled. But should we be keeping track of the labels of the original graph? Or is it an unlabeled view of both? I'm just trying to parse this distinction between labeling and distinguishing.
You should think of everything as being labeled. The Gn is an explicit graph with all the vertices are distinguishable vertices. And now we're thinking of a tiling of that graph Gn.
So the notation you use for the complete bipartite graph is that's up to isomorphism, but in fact, when you write K sub n, V, n, W, you actually mean the labeled bipartite graph.
There's
just as the set theoretic object where it's the complete bipartite structure between two labeled sets.
That's right. That's what I have in mind. That's right.
Okay, cool, cool.
Yeah, you should think of the vertices here as being labeled and the vertices there as being labeled, and then it's a...
Just in your two-dimensional examples, you were basically writing down unlabeled graphs above. So I was just trying to...
Yeah, you're right. You're right. That is a distinguished, right. That's why I didn't want to think too much about the two-dimensional examples here. But
sure,
let's
okay, good,
let's
good.
stick with this labeled version. Yeah, labels are always confusing to me. So if you see a problem, let me know.
Okay, great.
Okay. Okay, so let's let the omega n be the set of tilings. So really, it's just a tiling problem. We have some concrete graph. All the vertices are distinct and distinguishable, and we're just going to plunk in our tiles to cover the graph completely. All the tiles being disjoint, vertex disjoint. Okay, and of course, we had this weight function on our tiles. Each tile has a positive real weight, and we're going to use that to give a weight to the lifted tiles, well, the same weight to the lifted tiles, and therefore a particular tiling now gets a weight, W sub m, which is just the product over the tiles of the weight of the tile raised to its multiplicity, the number of times it occurs. Right, so it's a little... Let me try to distinguish between the tiles which are in the graph downstairs and the lifts of their tiles, and I'll try to call the ones above the lifts of the tiles. Right? There's a small number of tiles T. Those are the tiles in the base graph, and then each tile T gets used a certain number of times m of T. So I think hopefully it's kind of the natural thing this is the natural way to weight such a multi-tiling. And then, of course, the partition function, right, is the partition sum is the sum over all tilings of their weight, right? That's a natural thing. And if you like, we can put all the weights to be 1, and then this is just the number of tilings. Okay, and the first result is that there's a simple way to count the number of, to at least write a generating function for these quantities, the partition sum. And here it is. So we're going to associate to every vertex V in the original graph G a variable x sub V, right? And then we define a polynomial, right? What is this polynomial? It's a polynomial in the variables x, and it's the sum. There's one monomial for each tile, and for a given tile we make the product of the vertex variables, the product over the entries of that tile, and then times the weight. So if you like, it's kind of the generating function for the locations of the individual tiles weighted by their weight. Okay, and then the theorem, this is just a simple combinatorics theorem. When you exponentiate p, well, this is the thing, this is just a definition, but the exponent of p, if you think of p as now a function of the variables xi, its exponential is a power series, has a power series whose coefficients, exponential power series whose coefficients are the desired quantities, the partition sums. So the exponent of p is the sum over all possible choices of multiplicities larger than or equal to 0 of the weighted sum of multi-tilings. And then there's a factor, the n factorial factor, by which I mean the product of the factorials of the nv's. Right, so this is a sort of a multi-dimensional sum, but I've sort of collapsed the notation into a single summation over all the possible choices of multiplicities. It's really not very hard to prove. I thought I would just go through the proof. It almost fits on one slide here. I guess I can almost make it fit on a slide, so don't be scared. Scared is not the right word. Don't be concerned. This is really, I think if you're a combinatorialist and used to these things, you can sort of write a proof in one line here. But for those of us who aren't, let me write it out. right? Because somehow there's some general theorem about exponential generating functions counting multisets of objects. But let me just write it out here. Suppose we want to use a tile T with a certain multiplicity M of T. I mean, suppose we, I want to count the number of tilings of this graph, and rather than fix the multiplicities ahead of time and count the number of tilings, I'm going to rather than fix the multiplicities of the vertices, let me just fix the multiplicities of the tiles, and then at the end I'll be able to switch the summation, switch the order of summation. So I'm going to suppose we fix the multiplicities of the tile of each tile. Suppose we use tile T with multiplicity M of T. How many ways can we put those tiles in the graph? Well, for over each vertex here, suppose we have a tile, suppose my tile is just a triangle, for example. How many ways can I put M of T copies of that triangle in the graph? Well, over each vertex here, I've got some large number of vertices, n sub v. I have to choose a subset of size M of T, right? So that's some sort of binomial coefficient over each vertex. But once I've chosen the subsets for each vertex here, I have to choose a corresponding subset of size M of T, right? 3 here, 3 here, 3 here. Then I have to decide how to connect these things up, right? To make a triangle, I have to, if I choose this vertex, I have to choose which of the 3 vertices over here it connects to make a tile, right? And of course, I can once I've chosen that one and chosen that one, then the third edge is determined. Right, so you choose the vertices over each vertex, and then you split these vertex choices into the individual tiles, and you could do that in a certain number of ways, right? Because if you have 3 things over here and 3 things over here, you have sort of 3 factorial ways to identify them along an edge. So there's a certain number of factorial combinations along each edge of the graph. Well, along each edge of a spanning tree of the graph, if you like. And when you just multiply all those choices together, you find that the contribution for the vertex choices is just a product of binomial coefficients, multinomial coefficients, which uses the NVA factorials and then the other factorials in the denominator. And then you have to do the edge identifications, and there's a certain number of those. When you multiply those together, you get in fact, a very simple, there's some cancellation, and you get this product of the factorials of the multiplicity of the vertex multiplicities divided by the product of the factorials of the tile multiplicities. So that's the number of n-fold tilings when you use the multiplicities M sub T. And now you just multiply each of these combinatorial factors by the corresponding weight, which is the WT to the MT, and the XTs are just the variables. And then when you sum, you naturally get this exponential summation. Sorry, if I multiply, if I multiply this combinatorial factor times the weight and then sum over all possible choices of MTs, you just get that exponential. I hope that didn't go by too fast, but that's the proof. Okay. That's fine. So we have a.
So there's just been a question in the chat just asking if you could explain why the third vertex in the triangle is determined.
Yes. So what I mean is, maybe I said it wrong, but once you've chosen, suppose I want to lift this triangle into 3, has multiplicity 3. So I have to choose 3 vertices here, 3 vertices here, 3 vertices here. But then I have to identify which vertex over here corresponds to a vertex over here and a vertex over there. To make it into a tile, I have to split these triples of vertices into triangles. But once I've identified them along 2 of the edges, then the third edge identification is determined. So that was why there was a -1 over here.
And there's been a second question saying, would it be interesting to introduce a parameter for the inverse temperature?
Sure. But currently our parameters are just the weight. We do have parameters which are weights here. And if you like, you can think of those weights as having a temperature and as involving a temperature, right? Maybe each weight is e to the beta times an energy. That would be fine. And that does lead to some interesting effects, some interesting phase transitions. We'll see. Oh, yeah, absolute value of t. And now I can see the chat. Absolute value of t is just the number of vertices in the tile. Right. I can write that down. Number of vertices of t. Our paper, by the way, is mostly done, so hopefully you'll be able to read the final version shortly. Okay, now the goal is, we have this nice exact counting. We want to understand the asymptotics as n gets large. And just for the sake of the talk, let me assume that all the tiles have the same size. It's just same number of vertices. Right? Let's call this size delta, and we can adjust the argument in the other cases. Right? Suppose all of our tiles have delta vertices, and we're going to fix ahead of time the multiplicities at each vertex. Then the total number of tiles, of course, is the sum of the multiplicities divided by delta. That's the total number of tiles, capital K. Sorry, I used K twice, but this time K is going to be just the total. It's going to stand for the total number of tiles. And we're going to be interested in the limit as the number of multiplicities gets large. So we're going to let the multiplicities go to infinity simultaneously so that their ratios tends to some constants, which I'm calling alpha v, the ratio of the multiplicity divided by the total number of tiles. So that's, if you like, that's the fraction of tiles which cover vertex v. We want we want this ratio to tend to a constant alpha v. So alpha v's are going to be just some real number, positive real numbers now associated to the vertices, which sum, when you sum over all the vertices, to delta. That's sort of the natural condition on the alphas, and right. So this is the way in which we're going to take a limit. And then how do we compute a limit of this quantity zwn, right? This is our partition sum. That's the quantity we care about. Well, it grows like n factorial over k factorial. So if we multiply by k factorial over n factorial, well, sorry, it grows like n factorial. But if we multiply by k factorial divided by n factorial, this quantity, then we can extract that as a particular coefficient in p to the k. Let me go back, if you don't mind. Right, the partition, the grand canonical partition function is the exponent of p, but the coefficient of p to the k in this power series is the set of tiles where you use exactly k tiles. So if you use k tiles, that I should have done that a little bit better, right? But this thing is of course summation p to the k over k factorial, and this p to the k term corresponds to tilings which use exactly k tiles. And if all the tiles have the same size, then we know what k is ahead of time, so we don't have to deal with the exponent function. We can just take the p to the k itself and extract its coefficient, extract the appropriate coefficient to get the thing we want, right? How do we, right? So this notation means extract the coefficient of x to the n from p to the k. And of course we can write that as a contour integral, if you like. Now for large k, large number of tiles, we can evaluate this asymptotically using a saddle point method. I hope you're all happy with that. That's a standard technique for evaluating integrals when you have a exponent of a large constant, some function to a large power. And how does it work? You just look at you just find the critical point of the integrand with respect to the variables, the integration variables. So I just want to differentiate. I'm looking for a point where the integrand here is critical with respect to the variances in the x's. What does the saddle point method mean? Right here, we're integrating. Here we're integrating over some product of circles, but we can. But it's a contour integral, so we can change our curve, our surface of integration by increasing the radii or decreasing the radius. And the saddle point means you go to the correct radius where the fluctuations sort of die out, and if the curve, so you look for the radius where the surface of integration goes through a critical point of the integrand, and then you have a good estimation of the integral at that point. And there we have the critical point equations, which we can simplify to look like that. It's just some differential of p. Remember, p is just some polynomial in the x's, and right, you just do this differential, or you differentiate the logarithm, and this is the equation you need to satisfy to find that critical point. Oh, I guess here's a little calculation, right? If you go from this equation over to here, and you differentiate, you get that, which starts to look like that. So if we want to find the maximum, if we want to find, the value of this integral here, it's well approximated by just evaluating the integrand. I mean, to the exponential growth rate, at least, is just given by evaluating the integrand at the critical values, right? So we're looking for the x values, the xv values at the critical point here. And you know, it's not hard to argue that there's essentially a unique solution modulo some, okay, let me not talk about that here, but the solution is, let me say, essentially unique, essentially in quotes, that's an important thing, up to global scale. And then this limit, if I take this quantity, which I care about, the z, and I take the logarithm and so I multiply by k factorial over n factorial, I take the log, I divide by k, that has a nice limit. And that limit is given by this expression here, log p minus summation alpha v log xv. And here, by the x's, I mean the x's that satisfy the criticality condition. And we call that the free energy of the model. It's in some sense the limit of the logarithm of the normalized logarithm of the partition function. And okay, so now and that is the leading growth rate for the free energy of the model. And can we solve those equations? Well, you know, you might object that these equations are nonlinear and you're not going to be able to solve those in general. And yes, that's true. But the free energy here is a convex function of the x's. I mean, if you look at since there's some convexity involved, you can use a Legendre duality to actually solve these equations by minimizing a certain convex function. And in fact, essentially you want to okay, is it convex or concave? I've forgotten. Let's see. I don't think we need to go through the example here. Oh, okay. Let me just go through the example because just to make sure that and then. Okay, so let's just do a very basic, simple example. Here's our graph, a 2 by 3 graph, and we're going to let our set of tiles be the set of edges. So we're thinking of, if you like, we're thinking of a Dimer model, but it's kind of a multi-dimer model. So we're allowed to cover each vertex with multiplicity n, and we'll take n fixed, nv, some large constant, the same constant for each vertex. Okay, and we'll set all the weights to be 1, just for simplicity. Then our polynomial looks like this, right? This polynomial is the sum over all the tiles where the monomial has the x variables, and you know, there it is. X14 corresponds to this tile, X15 corresponds to that tile, and so on. And then the criticality equations here, the ones we need to solve, you know, you can just write them down here, and you can either solve that by hand, or you can use your computer to solve it, and then you find, here's the solution. It involves, you know, 1 plus root 5 over 2, 1 plus root 5 over 2, x1, 2, 3, x4, 5, 6. Those are, right, there's some symmetry which reduces the work. And then, you know, so you can get the free energy. It's just some number. It's pretty easy in this particular case, and you know, with a much larger example, your computer can do it very easily because it's just minimizing a convex function. But here's the kind of the interesting. Let me just state this theorem, and then we can pause for a bit. Let me give you the definition first. Suppose I have two different weight functions, W and W functions. So remember the weights, I have weights on my tiles, but there's some, from the weights determine the measure. And sometimes different weights determine the same measure. And in fact, there's a simple criterion for when two weights determine the same measure, right? And we say the two weight functions, W and W prime, are gauge equivalent if W prime of a tile is equal to W of the same tile multiplied by some function on the vertices. So if there is a function f from the vertices of the graph, which has this property that you just take the product of the function values at the vertices of the tile, and then you get the new weight function. And it's pretty easy to see, I didn't actually put in the proof here, that when you construct the probability measure, if you have gauge equivalent weight functions, they give you exactly the same probability measure. It's just some simple combinatorics. Right, that's what the limit says here. And you can interpret this. Sorry, now let me scroll back. I apologize for scrolling back and forth all the time, but if you look at the critical point equations now, you can interpret those equations in the following way. This is a theorem. For any feasible set of multiplicities, remember the alphas are the densities of tiles covering each vertex. For any feasible alpha, and feasible means can be realized by some limit of multiplicity of tileable regions, there is a unique gauge equivalent weight function. So you start with your original weight function W, you can find a gauge transformation F so that the new weight function W prime has the following property. So it's going to be gauge equivalent, so it has the same, defines the same measure, but it has the property that the sum of weights of all the tiles containing a given vertex is in fact alpha V. And I wrote that down here. So if for every vertex V, you look at all the tiles which contain that vertex, the sum of their weights is exactly alpha V. I hope that makes sense. Maybe I should do an example, but okay, I'll do an example. Since we're essentially out of time, let me savor the example till next time.
I think you can have 5 more minutes if you want to do the example now.
Oh yeah, okay. I don't know. It's either now or later, but right. Let me finish reading the statement. So the corresponding, well, this is the statement that there is a gauge equivalent weight functions which has this property that the sum of the weights of the tiles containing a vertex is the alpha V, and the corresponding gauge transformation function, this function F here, which moves you from one gauge to the other gauge, is the solution to the criticality equations from above. And here, let me just flash the slide. So it's kind of a well-known tiling problem, the Aztec Diamond. We're gonna right? There's some region in the Z2 lattice. Here's the Aztec Diamond of order 4. And I'm going to put, and we're gonna tile it with dimers again. So the dimers are just edges of the graph. So each tile just consists of 2 adjacent vertices. And we're going to initially have all the weights, just like before, all the weights are 1. All the weights are 1, and all the multiplicities are constant. And what the theorem says is that we want to, well, originally all the weights are 1 here. You can think of every edge has a weight 1. But we want to find a new gauge, so we want to change the weights in such a way that at each vertex, the sum of the weights of the tiles containing that vertex is equal to alpha in the limit. And I'm going to scale so that alpha equals 1. I have to scale by n or something. And well, here's the answer. Let me just show you the answer. This is the new, these are the new tile weights, and they're also the tile probabilities in the limit. So if you check here for this, in this example, the sum of the weights of the edges around each vertex adds up to 1, right? And the other property is that for every square, the product of the opposite edges in one way is equal to the product of the edges in the other way. So for example, 3/5 times 1/10, right? 3/5 times 1/10 is equal to 3/20 times 2/5. I hope. Yeah. A sudden doubt there. But those 2 properties characterize these numbers on the graph here. And those numbers are the probabilities of, I mean, the expected density of tiles that you use at each edge, right? So out of if you use k tiles total, then 9/20 k tiles are going to be covering that edge. Okay, so let me stop there, and I will explain this again at the beginning of the next talk. I guess we're going to take a break for 10 minutes or something.
Yeah, that's right. But first of all, let me just ask everyone to unmute themselves and thank you for the first talk. And then before we take a break, I think we've got time to have some questions. So if you have a question, either you can raise your hand, or you can, if no one else is speaking, just unmute yourself and speak up. Or if you ask your question in the chat, then I'll relay your question to Rick. So maybe while waiting, I have a couple of questions. So the first one is, you mentioned in your theorem that that applies if a tiling is feasible. Do you have a condition for checking feasibility?
Yes, that's yeah, I didn't want to talk too much about that, but not every set of multiplicities you put on the vertices are feasible. Right. For example, for this particular graph, it's a bipartite graph, and every tile covers like 1 black and 1 white vertex. Right. If you color the vertices, black and white. Right. So one condition for feasibility is that the sum of the multiplicities at the black vertices has to equal the sum of the multiplicities at the white vertices. And generally, the set of feasible multiplicities is in some sort of cone in this high-dimensional space. Well, it's some set of integer points in some sort of cone, and so it's a little bit involved to explain exactly what feasibility means. But it means a set of multiplicities which is realizable by at least 1 tiling.
But you can sort of classify or work out, write down that statement precisely, other than that a tiling exists, or.
Oh yeah, no. I mean, it's a linear algebra condition, right? Because each tile, right? There's a map from tiles into multiplicities, into the space of multiplicities, and it has to be you're feasible if and only if you're in the image of this linear map from Z, D into the space of multiplicities. So it's a linear algebra condition. I just didn't want to discuss it because it, it adds a little bit of complexity to the issue.
Okay, thanks. There's a question in the chat. It says, in the last example, where the property that products of weights of opposite edges in each face are equal, is that because it's true for all weights 1 at the beginning and preserved by gauge transformations?
Exactly. That's exactly true. In fact, for this particular example, two weight functions are gauge equivalent if and only if they have the same sort of biratios of opposite edge weights. I mean, you can check that, when you multiply all the weights at a single vertex by a constant, the ratio of this divided by that doesn't change. And so, and those are in fact the quantities which are invariant under gauge transformation. And so you can check that two weight functions are the same, are gauge equivalent if and only if they have the same biratios. And here all the biratios are 1, so that's the condition we need to check.
Okay, thanks. Are there any other questions? Would anyone like to ask, either raise your hand or write it in the chat?
So I have a question. So in this particular case for the Aztec Diamond, so the criticality equation, what is it? Is it at the end is product condition? Reduced, or is something more complex?
The criticality condition says that the sum that on the one hand you're gauge equivalent to the original weights.
Mm-hmm.
This is the statement of the theorem. You're gauge equivalent to this statement of the theorem here is essentially equivalent to criticality. The sum of the weights of the tiles containing each vertex is the desired constant alpha.
Mm-hmm. Yes, I was mentioning. So it is so this criticality equation star. I was referring to this.
That's right. I should have given it this. This is kind of an if and only if statement. You're critical if and only if, I mean, up to scale. These two conditions are satisfied here.
Okay, thanks.
This one, right.
Okay, maybe if I can just ask one more question. So you mentioned with the standard tiling models that there's applications, for instance, with phase transitions or atomic structures of, with the multi-tiling model, is there a specific application behind extending the single tiling to a multi-tiling setting?
Is there a specific application that we had in mind?
That's right. So is there a reason to generalize to multi-tiling setting?
Well, it's much easier, as you'll see. In the next talk, I will talk about the phase transitions and the crystallization phenomenon. But we didn't have any initial motivation. We just realized that all the questions we've been asking for random tilings for many years can be, have analogs here that are somehow easier. So really, we were just led by the fact that we could answer the questions in this generalization of the model.
Okay, so it's a mathematical motivation rather than a physical motivation.
Exactly. Yeah.
Okay, thank you.
Well, go ahead.
I'm not seeing any other questions, so maybe now's a good time to just pause if everyone wants to go and get a cup of coffee, and we'll resume again on the hour for the second talk. Thank you.
Hi, Rick. How are you?
Hey.
Good
Hey,
to see you.
Where are you now?
Bristol.
Okay. You have a position there.
Yes.
For you've been there for like a year now?
Yeah. Although it might argue it doesn't really make any difference where you are for the last year, but yes.
Sorry, I didn't hear what you said.
Yeah, I mean, you might argue it doesn't really make any difference where one is over the last year, but yes.
Exactly.
Yeah.
Exactly. We're all just faces on a screen right now.
But yeah, seems pretty nice place to be.
Yeah. Yeah. You're enjoying it?
Yeah, mostly.
Are you teaching?
Yeah. Yeah. So a bit challenging with the technological issues and so on, but
Of course, we're all challenged in the same way, I think.
I mean, I've found students are incredibly understanding and accommodating about it all. Yeah.
That's right. That's right. Me too. But it's still hard to give an exam and not have them just totally.
Yeah. Yeah. So with ours, we made it open book. So, I mean, unfortunately, it was the same exam that had been planned as a normal exam, but we had to make it open book. So they still had the same amount of time for it, but they're allowed to use the lecture notes and they're allowed to use anything they can find on the internet, but not actually talk to anybody else by any means.
Not post their question on Stack Overflow.
Yeah, exactly. So, but then you quickly find there are some certain questions. It turns out if you just search for the appropriate terms, you get a complete solution. So it became clear which those ones were.
Is Rebecca there with you?
Yes.
Is that your girlfriend's name? I forgot.
Yes. Yes. In both cases.
Have you heard from David yet recently?
I did see him at an online bell ringing event in the last month or so, and I said hi to him. No.
Okay. So the break was 5 minutes break, or should we start at 4? I don't remember exactly. Amanda.
I think now's a good time to start again. Yeah.
Okay. Okay. So just an announcement for next week. So we will have the talks of Frederick Bicklund and Yilin Wang. Okay. And so let us come back to the multi-tiling model with Richard Kenyon and with his second talk. So please, Richard.
Thanks.
So if you want to start, is it okay? Okay.
Yeah, good.
Okay.
Let's see. What else can I say about this model? I wrote down amazingly here because I don't really understand. This is nonlinear equations which you solve, and it's as far as I can. Well, there's no reason for the solution to be rational. It just worked out that way. For this particular example, it's kind of fun. Somewhere where did the? I thought I had another slide. Maybe it disappeared. There's an explicit formula for this. Is just the 4x4 diamond, but you can do the n by n Aztec Diamond too. Everything here is sort of every edge weight is a sort of a quadratic function of the position, depending on your coordinates. It's easy enough to write down. For those of you who know a little bit about dimers, there's a height function associated to a dimer model. And how does it work? I'm debating which slide to look at here. So there's a height function on the faces, you know, H, and it when you cross an edge, the height function increases by a quarter if there's a dimer covering that edge. This is for the single dimer height function. It increases by a quarter if there's a I need to draw a picture somewhere else. Like, right, suppose there's a dimer covering this edge, then the height function H increases by a quarter if the vertex to the left is white and you don't cross a dimer. And otherwise it changes by 3/4 the other way. And so this defines for each sort of dimer cover, this defines a height function on the vertices of the graph. And you can do the same thing with the multi-dimer model. It's just that you take in some sense the average change along each edge. And in this case, the average change to go from one face to another is determined by the corresponding edge weight here. Remember, this is not just the critical edge weight, it's also the probability that you put that the edge, I mean, it's not the probability is the wrong word, the expected number of dimers covering that edge, normalized. So if you put K total dimers, then 9/20 K dimers cover this particular edge. And so the height change, the height change is something you can also calculate in this multi-dimer model. Makes perfect sense in the multi-dimer model. And for this for the critical weights here, you can find that the height function is just the height function associated to it is just a simple quadratic function. Because all the weights satisfy some quadratic function of their position, it's easy enough to work out the height function, and it's exactly this equation here. Again, it's some sort of mysteriously simple thing, because if I change the region even slightly for more general regions, you can also, there's of course this, you can solve for the critical weights. They won't be nice rational functions. There'll be some complicated solution to some system of polynomial equations, but the height function does satisfy a sort of variational principle, just like in the standard dimer case, domino tiling case. And the sort of expected height function, for given boundary values like here, satisfies some variational principle where you minimize a certain surface tension, which in the single dimer model, the standard single dimer model, which I've studied for many years, has kind of a complicated formula. Here, the formula is somehow a little bit simpler. The surface tension sigma, which depends on the gradient of H, which has two variables, the gradient in the x direction and the y direction. It's a pretty simple function of S and T, the coordinates of the gradient. And somewhat remarkably, when you take this function and you can see that this equation here is a particular solution to the corresponding Euler-Lagrange equation for this surface tension function. Okay, let me move on. All right, now we started with the multi-tiling model. I showed you how to compute the free energy, the limit of the partition function, the log of the partition function. But now what we want to do is study the sort of internal structure of a large tiling, right? And in particular, each tile, when I have a random tiling, each tile occurs with a certain multiplicity. Each tile is downstairs in the right. We have k different. There's too many k's, but there is a finite set of tiles, and each tile gets lifted into the upper graph with some multiplicity, and that multiplicity is a random variable. And we would like to understand that.
So Richard, sorry, before starting this new subject, so a participant has asked if you can. So could you give give some words about the surface tension? What is here the surface tension? Can you comment it? So I think
Okay. Right. So when I let's see. Once you understand the height function, so each time you have a tiling of this region, it has this height function, which you could think of as a way to represent the tiling as a surface in 3 dimensions, and it has certain boundary values. So for each random tiling, we get this surface spanning these boundary values, and the surface tension measures how much that surface likes to be tilted or prefers to be horizontal versus tilting. So it's just a way. The surface tension is a tool which is used to count the number of tilings with particular boundary values, like this one, right here. When I tile this particular region, its height function corresponds to some sort of curvy surface there, and how much does the surface pay in entropy to have a tilt, right? It's the sort of the entropic cost of having a tilt. That's the surface tension. And of course, the theorem, which goes back to Kohn and Propp and myself, is originally for the Dimer model, is that the typical surface you will see if you take a large random tiling is one which minimizes the total surface tension, right? And in this case, this multi-tiling model also has a surface variational formulation of this type, where what you see as the limiting height function is the one which minimizes this surface tension, except the formula for the surface tension here is simpler than in the single Dimer model. Does that help? Let me go on, because I didn't really want to talk too much about the surface tension. I want to get to the more immediate, let's say, applications of this stuff. So I may have alluded to this already, but we're going to fix the density alpha. So there's some feasible densities. You can think of that as fixing the multiplicities of the graph. The densities of the fraction of multiplicities over each vertex, and we're going to solve the critical equation. So let's let W be the critical weights, right? So then this polynomial P, right, looks like this. This is our same polynomial, but we can use the W's now to be the critical weights. And if we think of this, we can think of P as a probability generating function for placing a single tile, right? Because there's one monomial for each tile. And so we can think of the following process. We take our graph, we pick randomly a tile from our bag with the weights W, and we just throw it in this location. And then we do it again and again and again. And so it's like doing a random walk, right? So each P corresponds to one step of a certain random walk, and after K steps, the configuration is determined by P to the K, right? So this means we've placed K tiles. Each one is sort of IID chosen with respect to its critical probabilities, critical weight function. And right, so after placing K tiles, each tile T is right. You should think of each tile T as being, has some probability of being placed at each time. It's like having a Poisson number of the number of times we place each tile is like a Poisson random variable with a certain mean, K times the weight. Here, yeah, I should scale all the weights to sum to 1 to make it a probability distribution. And of course, when K is large, these Poisson random variables tend to a Gaussian distribution, right? So if I subtract their mean, yeah, maybe I shouldn't have written it this way. But, the denominator here is not necessarily the standard deviation. It's just some scaling factor. But once I subtract the mean and I scale appropriately, these converge to a multi-dimensional Gaussian random variable. Let's see, what should I, no, I forgot to say something here, right? You take the, let me start over briefly, right? You have your bag of tiles, you iteratively pick a tile and you plunk it down on your graph, and you do this k times. And, but now, when you do that k times, you won't get exactly the correct multiplicities. So you have to then take that, the number of times each tile is used as some Gaussian, but then you want to restrict that Gaussian to the appropriate, there's a linear restriction you put on that Gaussian, which is to restrict it to the subspace where the multiplicities add up to the desired multiplicities given by alpha. Right, so what happens is that we have these sort of essentially independent Gaussians at each tile, for each tile, but then we have to restrict to the subspace, right? We're trying to make at the end of the day, we want to make an n-fold tiling. We want to restrict to the subspace where the multiplicities sum to n at each vertex. But it's true that when you take this bunch of independent Gaussians, I mean a multidimensional independent Gaussian, and you restrict to a linear subspace, it's still a Gaussian. And that's a nice feature of Gaussians. When you restrict to a linear subspace, it's still a Gaussian random variable. Or you condition on being in a subspace, it's a Gaussian random variable. And when you do that conditioning, you can write down the covariance function becomes an interesting function of the original Gaussian and the subspace. But you work that out. That's sort of kind of a standard thing, which I won't do here. You take this process. When you restrict to the appropriate subspace, you get a multidimensional Gaussian, which has a particular covariance function, which you can actually write down. And I think as we all realize that, the multidimensional Gaussian is of course determined by its covariance function. And in this case, the covariance function is a kind of a simple matrix. In fact, it's a projection matrix onto a certain subspace, which maybe I won't try to describe here, but it has the following form, and what I want to talk about is what the components of this covariance matrix is. Because it involves a certain Laplacian operator, which we call the tiling Laplacian. So let me explain what these three things are: D Laplacian and D star, Laplacian inverse. So here D is just the adjacency matrix between tiles and vertices. So if you like, maybe I should write that down. So D, TV is, 1 if the vertex is in the tile and 0 else. Right? It's just the incidence matrix between tiles and vertices. And then the Laplacian matrix here has this formula. Well, D star is just the transpose of D. And so you take D star times W, the diagonal matrix of weights, and then D again. So the Laplacian is an operator on the space of vertices of the graph. This is the graph downstairs, the small graph, and we call that the tiling Laplacian. It's very similar to the standard graph Laplacian. In fact, it is the graph Laplacian if the tiles are, well, it's not, what do I want to say? Okay, never mind what I was just going to say. It's closely related to the standard graph Laplacian if the tiles are just dimers. But if the tiles are more general sets, then it's some variant of the graph Laplacian. It is kind of a graph Laplacian for some more complicated graph associated to the underlying graph. Okay, but it is a positive, definite, symmetric matrix. Sorry, at least positive, semi-definite, symmetric matrix associated to the graph. And oh yeah, here's a formula, right? the UV entry, if the UV entry of this matrix is just the sum of the weights of tiles which contain both vertices U and V. Okay, so in order to sort of understand this theorem, all we need to understand the multi-tiling model, in the limit of large multiplicities, it's a Gaussian model, and all we need to do is understand the covariance matrix, which has a quite explicit formula in terms of this graph Laplacian and the adjacency matrix D. Okay, so now we can go to some examples, and I want to sort of illustrate some examples which show you how much interesting behavior this model has, right? Because I think we sort of get if someone says, "Oh, this is just a Gaussian process," you think, "Okay, I understand a Gaussian process is kind of a boring thing. It's kind of the most boring probability measure you can imagine." Except for maybe a Bernoulli process. But actually, this model still has some interesting behavior, despite the fact that it's Gaussian. Okay, let me say it that way. The examples are going to build up in complexity. So let's start with an easy example on the Zn, Z mod NZ, a cycle. The underlying graph is just going to be a cycle of length n. And I'm going to consider tiling it with bars of length 3. So, right, a tile is a sequence of 3 consecutive vertices around some cycle. Now, just again, for simplicity, I'm going to set all the multiplicities to be the same, capital N. And so and xi, sorry, maybe I should have written more on this. So xi is the multiplicity of the tile at I. So let's call this I plus 1, I plus 2. Right, each tile, I can index the tiles by by their left endpoint, if you like, around the cycle. And the condition on the multiplicity of the tiles is that the sum, right, for each vertex here, maybe for this vertex here, no, sorry, my mistake, undo. For this vertex here, vertex I plus 2, there's 3 different tiles which cover it, the tile at I, the tile at I plus 1, and the tile at I plus 2. And the sum of their multiplicities has to add up to n. That's the condition. Right, but right, so there's a simple linear constraint here. This is a bunch of linear constraints on the multiplicities of the tiles. And if this cycle here has length n, which is not a multiple of 3, if n is not a multiple of 3, then these equations have a unique, if you think of these as equations for the capital X's, there's a unique solution, which is n over 3. So it's in fact, there's only one way to put the tiles in. Sorry, there's only one choice of multiplicities which work. And so all the multiplicities are exactly n over 3. And in fact, therefore, the covariance matrix is 0. The covariance between the multiplicities is 0. The probability measure concentrates on a single configuration. It is symmetric, sorry. I can see the chat. You're complaining that this matrix is not symmetric.
Yeah, I was going to ask the question just at the end of the example.
Maybe it's because I'm missing a term. Let me think about it and I'll come back to you. Oh, maybe I missed, oh yeah, so.
But
I think maybe I should have written like that.
Mhm.
Then it looks symmetric. I apologize. I'll try to fix that at some point. Let's see. Oh yeah, so going back here to this example. So if n is not a multiple of 3, then there's a unique configuration of densities, nothing happens. But if n is a multiple of 3, then when you solve these equations, you find that there's some sort of 3 periodicity. There's a 1-parameter family of solutions. Sorry, there's a 2-parameter family of solutions, but the xi and xi plus 3 are the same. So really, instead of having sort of n Gaussians, when you restrict to the subspace, you have only sort of a 2-dimensional Gaussian space, and the covariance matrix has rank 2. This is my covariance matrix here. And so what you see is that the system is sort of crystallized, if I can say that. Knowing the density of tiles at a given location determines the density of tiles arbitrarily far away in terms of multiplicity of 3, right? An arbitrary multiple of 3 away from it. So let me sort of, I mean, it's not obvious where this matrix comes from. Let me go through the calculation because I will use it immediately for the slightly more complicated cases. So in order to, right, so we have a formula for the covariance matrix here, up to errors on my part. What we need to do is compute this operator delta inverse d star, and but in the case of a graph like this, which is a cycle, there's some, right, the graph is symmetric. We can use a Fourier basis to deal with these operators on a symmetric space, on this graph, which has this group of symmetries, right? So if I let Vz be the space of functions, which are essentially eigenvalues for the translation operator. So you take z to be an nth root of 1, and then you think about you consider the space of functions on z mod nz, which have the property that when you rotate by 1, they multiply by z, this nth root of unity, right? And the space of all functions can be decomposed into these subspaces Vz. Those form a different basis, a Fourier basis for this space of functions. And then you can see that the Laplacian, the tile Laplacian, preserves these Vz spaces, these 1-dimensional Vz spaces, and the corresponding eigenvalue is just looks like this, right? This is right. This is like the characteristic function of a tile, right? A tile has 3 vertices, which are at I plus 1 and I plus 2. And because the Laplacian has some symmetry, is a symmetric matrix, it's d star essentially. This is the eigenvector for the Laplacian. And in fact, d also, you can think of d, right? D is an operator from the tile space to the vertex space, but if you identify them, then you can also consider d to act on Vz by multiplication by this, and d star acts by multiplication by that, and so on. Once you go to the Fourier basis, it's fairly easy to figure out what this operator does, and it corresponds to multiplication by n if 1 plus z squared is non-zero and it's 0 otherwise. And so when you take I minus that, it just becomes to a 2-dimensional projection, and it's a projection onto the subspaces, the sum of the 2 subspaces for the primitive cube roots of unity. So that's essentially where this formula comes from, and that's why you see this sort of periodicity, is that you're projecting onto a lower dimensional subspace, which has this periodic behavior in Fourier basis. Okay, this, you may be thinking this is just sort of this example is a little bit too trivial. So let me soup up the example a little bit. by, I'm going to consider bars of length 3. So I'm going to think about the same graph again, Z mod NZ, a cycle graph, still in one dimension here. But let me take bars of length 3, and I'm also going to allow singleton tiles, so a tile to just cover a single vertex. Right, so on my long cycle here, right, I can tile with bars of length 3, but I can also tile with single vertices. So you can think of the single vertices as like defects in the tiling. So if I add some positive density of defects, then suddenly I no longer sort of feel the boundary conditions as strongly. So maybe you don't notice that you're part of a cycle, right? So let's consider this fraction of singleton tiles be epsilon, and you might object that now my tiles no longer all have the same size, but everything I've set up to now can be adjusted so that the tiles have different sizes, and it's not you can prove everything I did with tiles of different sizes. Okay, but now I'm going to take epsilon to be a small positive integer, and let's have it be fixed. But yeah, so maybe I should just ignore this part for now. Let's have it be a fixed small. It's not, I said integer, but I meant small real number, positive density of tiles. And then when you work out, you can do the same Fourier analysis, and you work out the covariance matrix between x0 and xs, and these are some sort of normalized as above. Then it looks like this. It's again given by the Fourier coefficients of a certain function, and here the function has this same denominator as before, 1 plus z squared times 1 plus 1 over z plus 1 over z squared plus epsilon, and you can think of this as epsilon times 1, epsilon times 1, where 1 is this corresponds to the singleton tile, and this term corresponds to the tiles of length 3. And so that's an explicit formula for the covariance matrix between the tiles, between the density of, this is for the density of the length 3 tiles. I didn't say that. You have a length 3 tile at the origin, and you have a length 3 tile at some distance s away from it. So this length 3 at the origin, at 0, at s, right? So right, is that I should have said that. So here's the origin here, and over here I have a point s, and I want to know the random variable which tells me how many of these tiles I have, versus the covariance between the number of tiles here and the number of tiles there. And here's an explicit formula, and it involves the Fourier coefficients of this kind of interesting function here. This function has, if epsilon is 0, this function has a pole somewhere along the unit circle. And the fact that there's an epsilon means that pole gets sort of mollified a little bit into like a bump function. And it's not hard to work out the asymptotics here as a function of epsilon, as epsilon is very small. And you can, here's the formula, right? You still get this sort of periodic behavior, cosine 2 pi s. So it depends on whether s is a multiple of 3 or not. And then there's some factor 1 over square root of epsilon in the numerator, and then there's this sort of exponential decay with the square root of epsilon in there, right? So as s grows, the covariance decays to 0, but it's still, you can still see that periodic behavior. In the limit, as epsilon goes to 0, the exponential decay becomes weaker and weaker, although, and there's also some sort of blow up. It's kind of an interesting trade-off. Okay, let's go on. Let's move up a dimension here. And now I'm going to tile Z2 or maybe some torus, and I'm going to take the my tile is just going to be a copy of this L triomino, and I'm not going to allow any rotations. Just face up. I mean, this orientation of triomino, this L shape, right? But I'm also going to allow a small density, like before, of monomers. So one by one tiles. Which I'm going to think of that density as very small. And then you can run through the same analysis as we did using the Fourier analysis, and you get an explicit formula for the covariance here, which is given here. And this is some sort of, I should have written asymptotic 2 here or something. It's not an exact form. This is the, hang on. Well, in an appropriate limit, this is the correct formula. In the limit as n gets large, I mean, I said Z2 here, but really what I mean is Z2 mod n Z2, but then I'm going to take n to infinity, and this is the red box is the formula as n goes to infinity. And that's an exact formula, but and now you see that you see the same kind of thing, right? It's the Fourier coefficients, the covariance here between a tile at the origin and a tile at a point ST. Right here, where there's one tile at the origin, and the other tile is far away at distance s comma t. Is given by the Fourier coefficients of this similar kind of function, right? It's in the denominator I get epsilon plus this sort of characteristic polynomial of the tile times the characteristic polynomial of the tile conjugate. And this integral can be worked out as some sort of Bessel function, right? And there's still a periodic prefactor, right? This is the prefactor here is a periodic function of the position s and t, and there's some. But then this Bessel function in the limit epsilon goes to 0 looks like log epsilon plus some lower order terms. And I think I have a picture here. Yeah, here's a picture of this is the, right, here's S and ST. And there's the tile at the origin here is fixed, and then I'm plotting the covariance here. And this is when epsilon is 0.001, you can see that, so orange means large value, and blue means small negative value, I mean, large negative value. And you can see that as epsilon gets smaller and smaller, you converge to this sort of crystal shape, right? The covariance becomes, they're perfectly correlated if they're along the same diagonal. And if the diagonal is shifted by 1 or 2, they're perfectly they're not perfectly anti-correlated, but they're anti-correlated. And then they're again perfectly correlated if you shift by a multiple of 3 diagonally.
So, sorry, Richard, I have a question. So in this model, you have a capital N, which is the vertex multiplicity, and
Yes.
a small n. So you first take the limit capital N going to infinity, and after the limit small n going to infinity?
Right. That's right. You have to be careful about the order of limits. And I've been a little bit glib about talking about that. But yes, you only get the sort of Gaussian behavior. You have a finite graph, then you take the capital N, the multiplicities to infinity, then you get this Gaussian behavior. Then once you have the Gaussian behavior, then you can let the graph itself get large.
Mm-hmm.
So really this is the limit as capital N goes to infinity first, then little n.
Okay, thanks.
Yeah, and there's also a limit of epsilon. So there's, epsilon is also going to 0. But right, so this is this picture is sort of, oops, for a small but constant epsilon as little n goes to 0. As little n goes to infinity.
Okay, thanks.
But I think, you know, the point I'm trying to get across is that even though this model is Gaussian, you can see that in the limit there's sort of different phases, right? There's the phase when I mean, there's right. I should mention that, you know, this tile can tile the plane periodically, but there's sort of 3 different periodic tilings, which are all translates of each other by 1, -1, comma 1. Right, so if you put down a single tile, if you sort of force a single tile, then all the tiles around it will try to line up in that same crystal structure. But if you put the tile at a slightly different location, you'll get a different limit. So there's sort of 3 different measures, limiting measures here. Okay, so that worked out pretty nice. Let's we can try to make a general statement of that type. Okay, so here's an attempt at a statement, right? Suppose I take a polynomial of t, and let's just on Z2. Our graph is Z2, and we're going to take a small density epsilon of monomers, just like the previous example. Then here's the theorem. The covariance function in the appropriate limit is given by the Fourier coefficients of this function, 1 over epsilon plus norm of p squared, where p is this characteristic polynomial of the tile. It's the sum of z to the I, u to the j, where I and j are points in the tile, just like in the previous example. Where in the previous example, if you don't mind, it's you know, this quantity p is, you know, 1 plus z plus u. It corresponds to the 3 squares inside that monomer. But this makes it an interesting question, right? Because this function here, of course, if p has a 0 on the unit torus, then there's some sort of peak in these in this 1 over epsilon plus p squared, and that has some effect on the Fourier coefficients, on the decay of the Fourier coefficients, right? And so the conclusion here is that the sort of leading asymptotics of the covariance function depends on the type of the zeros of this characteristic polynomial p on the appropriate torus, right? Because the way you compute the Fourier coefficients is to do some integral, where you have to integrate this, you know, z to the and when p has a 0, that means that this you know, the Fourier coefficients are somehow controlled by the zeros of p when epsilon is small. And so there are several different behaviors depending on the zeros of the characteristic polynomial here on the torus. Right? In the simplest case, like the case we just did, the L polyomino, this guy has only simple zeros on the torus, right? The only way to make 1 plus z plus u 0 is to have the z and u be the 2 sides of an equilateral triangle. So the cube roots of unity, right? And in those cases, the correlations decay, blow up like log of epsilon. The covariances blow up like log epsilon. But there are some you get a very different behavior if you have different kinds of zeros. For example, if my tile is the square, you know, the 2 by 2 square, right? The characteristic polynomial looks like that, and then we get a whole line of zeros on the torus, right? How do you make this guy 0 on when z and w have modulus 1? Well, z could be -1 or u could be -1, right? There's a whole circle of zeros on the unit torus, and that makes the leading asymptotics of this covariance function very different. In fact, it's got a 1 over square root of epsilon times log epsilon behavior. Epsilon, remember, is the density of monomers. And this also affects I think I've got a picture. Oh yeah, here's the case of the square. When epsilon is 0.001, you see this kind of interesting sort of checkerboard behavior. It's still true that as epsilon goes to 0, you see this sort of interesting lattice behavior. I don't really understand this picture, though. I mean, I can do the calculation, but I don't have a sort of a heuristic explanation of why this is the answer. Because the square, a 2 by 2 square can tile the plane in many different ways. But apparently, when you think about multi-tilings, there's some sort of preferred, 2 different preferred measures. But let me talk about the next example, right? The examples get more and more crazy. This is a very simple, also a very simple polyomino, right? The plus polyomino here. Sorry, there's some construction outside my office. I hope you guys can still hear me. Here the characteristic polynomial looks like that, right? It's just the sum of powers of z, 1 for each square. And there on the torus, we get a whole curve of zeros. I don't know how that, maybe I should draw a little picture of that. So on the unit torus here, where, here's phi and theta going from 0 to 2 pi. There's this whole curve of zeros for this polynomial p, and the corresponding Fourier coefficients decay like 1/square root of epsilon. So it's different behavior than the previous 2 examples. And let's see. Oh yeah. So here's the picture of the covariance function as a function of s and t. And you can see, well, what happens is that there's no crystal, right? It kind of decays, but it only decays slowly, like polynomial. That's like square root of the distance. Well, I'm sorry, 1 over the distance and a square root of epsilon. So the covariance is actually decay to 0. So you don't get any sort of crystallization phenomenon, but you still see a sort of long-range behavior, long-range order of some type. All right, and what else? What other examples do we have? Well, there are, easy cases like this one where there are no zeros on the torus. And if there are no zeros, then the decay is exponentially fast. Right? There's some Laurent series expansion, and the decay is determined by the distance to the nearest 0, but with an exponential rate. So there's this sort of a exponential decay of correlations. That's what we would say. Here's one slightly more mysterious example. This example, for this polyomino, again, its characteristic polynomial, which you can write down, does have simple zeros, but the zeros have irrational arguments. I mean, the arguments are not rationally related to each other or to pi, which means that you don't get any sort of periodic behavior. Even though you get a crystal, in the end, you don't get a periodic behavior. You get a quasi-crystal. The correlations don't decay, but they have this sort of a quasi-periodic behavior. So right here's the sort of the plot. Right, remember the orange means a almost perfect correlation, and blue means negative correlation. Right, so yeah, in the limit as s and t gets large, the covariance function just looks like a cosine of some irrational angle times the log term. So you get this long-range correlations, but not periodic. That's a quasi-crystal. And just to end my list, this is not supposed to be an exhaustive list either. For one thing, I restricted myself to 2 dimension. There's no reason to restrict yourself to 2 dimension. You can go to ZD, and you can get even more bizarre behavior. We haven't really even explored the full extent of the kind of behaviors we get. So I think there's still a lot to explore in this model, and it seems reasonably robust and works on in many settings. It doesn't even have to be a periodic graph like ZD. So I think there's lots still to explore, and I hope you appreciate the I should stop. Thank you.
Thanks a lot. Sorry, I'm a little lost with the comments. I don't see the comments. Amanda, can you unmute the people? Okay. Okay, and now I'm okay. I've done. So sorry. So I would ask everybody to unmute himself, themselves, in order to thank all together Richard for these very nice talks. Okay, so we have 5 questions. Is there some question? So I have a question concerning these last pictures. Do they solve some? Do you expect that they can be characterized by some variational in some variational form? So do they correspond to some minima or some functional?
These last pictures?
Yes. So the behavior with yes, the pictures representing the limit of vanishing epsilon.
Right. Well, they are Green's functions for a certain kind of Laplacian operator. Maybe that's the right way to describe them.
Mm-hmm.
But there's this parameter epsilon. You can think of epsilon as some sort of temperature, I guess, right? Because epsilon sort of represents the density of defects in the tiling. And when epsilon goes to 0, it's kind of like taking the temperature to 0. And then, in the limit of 0 temperature, you do get this crystallization phenomenon. I don't know that because they are Green's functions for Laplacian, right? They do have some sort of variational formulation, but I think the simplest way to say is to just say that their Fourier coefficient. I'm just plotting the Fourier coefficient, the Fourier coefficients of this very simple function here. This.
Yes.
Characteristic function.
Okay, thanks. So there is a participant, Shapir, who would like to ask a question. So please.
Yeah. Okay. I am coming from a physics background, and I know several problems in physics were solved by mapping them to Dimmer's representation. The most famous one is the 2-dimensional Ising model.
Yes.
But there is also Ising model in a field, etc.
Yes.
I am just asking myself, or ask you, if you were able to solve any problem that physicists were not able to solve before, to provide some exact solution to some interesting physics problem by your method?
Yeah. Yes. Okay. That's a perfectly good question, right? I understand the Ising model in 2 dimensions, and there's a 3-dimensional is very, very important problem. These models are, I would say, variants of those models. So I can make a variant of the Ising model. The Ising model can be represented as a random tiling model, right? Ising model just means you have spins plus and minus, and you can encode your tiles in such a way that one kind of tile represents a plus and another kind of tile represents a minus with some interaction. So you can encode it as a random tiling, and that's still, but then when you make it into a multi-tiling model, right, you take some sort of Gaussian limit, then you can solve it using the same techniques. But of course, it's not telling you about the original Ising model. And the interesting thing about the Ising model is that there's some interesting phase behavior as you change the temperature. In this multi-tiling model, things tend to be sort of analytic. So you don't expect phase transitions as sort of internal phase transitions as you vary the parameters.
But it's fine.
Go ahead.
No, you start with a multi-tiling, but the end the solution you find some of them are perfectly periodic and would represent a discrete kind of, one dimmer per site or per bond or whatever.
That's right.
Maybe I'm mistaken. Maybe the solution is different. But when you present your Fourier transform and you go to the limit, you saw some model which are perfectly periodic.
Yes.
So we can represent also the situation of very few types.
Yeah, I agree. There are. I sort of tried to present these phase transitions in this model, and I think physicists should be interested. I hope that physicists are interested in this as well, because it's, even though it's a Gaussian model, there are these it's sort of a Gaussian model in the limit where you get to phase transitions. Mm-hmm. That's not the right thing to say, but there's more to be explored here from a physics point of view, I believe.
Oh, thank you.
Okay, thanks. Is there any other question? So I have another very basic question. So in the characteristic, so just in this slide, so so we have P, the characteristic polynomial associated to the tile, but in the slide before there was the definition, but it depends how you locate the tile on Z2. So yep. Which is the rule where because otherwise you change the exponent. So if you translate the tile, you change the exponents.
Right.
So, right. So I suppose there is a convention.
Well, I'm not sure I understood the question, but the covariance, this covariance is a function of S and T, mm-hmm. and that as a function of S and T, it's exactly the Fourier series of 1 over epsilon plus p squared. This is sort of the definition of the Fourier series of that thing. So this covariance function is the Fourier transform, I mean this discrete Fourier transform of this 1 over epsilon plus p squared thing. Was that what your question was about?
No, but don't worry. Maybe okay. This I don't want to insist. Okay.
There was a question in the chat.
Okay, let's see.
Could the behavior of zeros be described in a more continuous form? Computing the Fourier series of a function, of a singular function on the torus is a very old problem, and I'm not an expert, and we're not experts on it, but finding the Fourier series of a function of this type, which has some zeros on the torus, that I think is a reasonably well studied problem in analysis. And if you talk to an expert, he will tell you what the growth rate looks like as a function of the type of zeros. But what I want to indicate is that we don't yet sort of know. I mean, I suspect that, but with complicated tiles, more and more complicated tiles, you can get essentially any behavior here that's feasible. And I think if I understand the question correctly, as a function of the type of zeros you get on the torus, right? What is the growth rate here? That's a well-studied problem. What we haven't sort of understood quite yet is, for our particular kind of restrictions, right? We have some restrictions that our tile is a polyomino of some type, maybe connected or not. Which types of zeros can we get?
Okay, thanks. Is there any other question? Okay, I don't see other questions in the chat. So if there are no questions more, I would ask again people to unmute themselves so that we can thank Richard for these very nice talks all together.
Thank you.
So thanks a lot. So it's done. I stop recording. Okay.